Yes, this sort of goes back to some of the stuff we learned in chapter 6, where there's a lot of different ways of looking at solutions, a lot of different ways to calculating concentrations. Molarity is something that we've been obviously interested in doing because we know that reactions take place in molar ratios. And so if you're doing a reaction, it's really important to know what the molarity is. But in a lot of other situations, when we have solutions, we're not actually going to be doing a reaction. And in those circumstances, it's not so important to know what the molarity is. And it's more important to know things like, well, how many grams of solute are in this solution? What's the percentage of volume? For instance, if I'm mixing two liquids together and I'm not going to be doing any reactions with it, it's more important to know what's the percentage. Like with your bottle of rubbing alcohol, how much alcohol is actually in there? 50%, 70%. That's more important to know. And so one of the things that we're going to do today is to use a lot of these different measures to try and figure out what the concentration of a solute in a solvent is. And one of the virtual labs that's on Chem Collective, which is one of the places I really like to look for these virtual labs, is calculating the concentration of sucrose. Unfortunately, as I realized when I was sort of putting together the lab, we don't really have sucrose in cola anymore. What do we have instead? What's the typical sweetener in not a diet cola? There's lots of different ones, but again, regular soda. What's the typical sweetener now? Ryan, right? Corn syrup, high fructose corn syrup. So that's one of the reasons people have been drawn to sort of so-called more natural sodas that actually use cane sugar made from sugar cane or sugar beets. You get the same sugar out of them. And so looking at the concentration of sucrose in cola, you're going to have to look at so-called Mexican Coca-Cola, because that's why a lot of people prefer, that's why you see Mexican Coca-Cola in a lot of stores, is because it doesn't have high fructose corn syrup in it. It's got the good stuff. It's got the real stuff in it. And people can claim they taste the difference, or they got a thing against high fructose corn syrup because I think it causes diabetes more than other sweeteners do. Not going to get into all that. But so one of the questions I put in here is, can you figure out what the concentration of sucrose in Coca-Cola is? And you're not going to be able to find that out for Coca-Cola made in America. So you may have to do a little bit of digging. I'm going to do a little bit of digging too, and see if we can find out what the concentration of sucrose is in Mexican Coke. I'm kind of curious, because one of in the introduction to this lab online, they talk about the so-called secret formula for Coke that supposedly only like 2 people know. So it's under lock and key in some bank vault somewhere. But someone thinks they figured out how much sugar goes in it, and they call it, I think, what do they call it? The X, formula X. So one of the first things we're going to do is actually make that and see how much sugar that is, make the solution, and then we're going to make a standard curve. Now, can anyone tell me what a standard curve is? What's the use of a standard curve? Has anyone even heard the term standard curve before? Not a word. What do you think it means? If you had to take an educated guess.
A curve or a graph that you use against other graphs, like that's the standard.
So well, yeah, right? So what would you use? So what is it? What would you actually plot on a standard curve? So you're right. You use it as a standard to measure other things. So what would you actually put on a standard curve? What are you plotting on it? Just in general.
Measurements.
Mm-hmm. Measurements of what? That's exactly right. You're plotting measurements of something. But what is it? Measurements of what? Yeah, concentration. Okay, that'd be one thing. But what do you have to, if you're going to plot something, what do you need to know? So if you're going to plot a measurement of something, so y would be the independent variable with the measurement.
Does it look like I fixed the solution, Francis?
What's on x? What's on the x axis? What am I plotting?
Volume. X is volume.
Could be volume. What else could it be? Like Ariana said, it could be concentration. So it could be volume, could be concentration. But what am I really getting at? There's something, you measure something, so you plot the measurement against something else. Could be the volume, could be the concentration. But I'm trying to figure out a way to put it that doesn't give it completely away. What things would you be, what sort of things, volume, concentration, what about those two things do they have in common? Yeah, it could be density. It could be plotting density against.
They're qualitative?
They're not qualitative, no.
Quantitative?
They're quantitative, right? So you're making quantitative measurements. Those go on the y-axis. You're also taking quantitative something else going on the x-axis. And then, yeah, it could be density, could be volume, could be concentration, could be a lot of different things. But there's something that they all have in common. What would they all have in common? They have to be blank.
Denominator?
Well, it's in the denominator when the slope of that line would be y divided by x. So yes, the x would be in the denominator. But I'm looking for something else. Any of those values that you plot on the x-axis have to be, in order to plot something, that value has to be what? Measured. Actually, your measurement is on the y-axis. What am I putting on the x-axis? Yeah, so Ryan mentions that generally when you think of a standard curve, you're looking at light passing through a solution. So you're plotting the absorbance of that solution against the concentration of that solution. But are these random solutions or Are they specific types of solutions? Like in this instance, we're going to be making a series of solutions. What are we going to know about those solutions? Because we made them. It's hard to try to figure out a way to ask the question without giving you the answer. Known concentrations. There you go. Yes. You have to, what a standard curve is, and I will just draw right here on the, what a standard curve is you're plotting the measurements of a series of things. That could be volumes, that could be concentrations of solutions, that could be densities, could be a lot of different things, but they're known because you made them. That's the secret of the whole thing. So in this instance, we are going to make a series of solutions with known concentrations of sucrose. And so we're going to plot the density on the X because we made those solutions. So we're going to know what the density is. I'm sorry, we're going to, we're going to measure the density. Duh. We're going to measure the density because we don't know what the density is against the concentration. So we're going to make solutions of known concentration, 5 grams per 100 mils, 10 grams per 100 mils, 20 grams per 100 mils, 40 grams per 100 mils. And we're going to make those solutions, and we know what the concentrations are because we made them. So we're going to know what they are very precisely. Then we're going to measure the density. Now the density is going to be the independent variable. The dependent variable, the dependent variable. We don't know what the densities are going to be. We're going to have to measure those. But then when we plot the concentration versus the density, we should get a line that sort of looks like this. And there should be a relationship between the concentration and the density. So the more concentrated it is, the denser it is. And that makes sense, right? Because if we think about, I think one of the examples I gave was like drinking water and seawater. It's been known for like thousands of years that seawater weighs more than drinking water if you take the same volume of each one. So if I weighed a liter of each one, the seawater would weigh more because there's stuff in there. There's a lot of solute in there that takes up space and has mass that's denser than water. On the other hand, if we're measuring the density of like alcohol solutions, so if I have ethanol plus water, ethanol is less dense than water. So the more ethanol I add to water, the less dense it becomes. And so what I would see under those circumstances is something that looks like this. The density actually going down the more ethanol I added. And people use that to measure the concentration of ethanol to this very day. You know, brewers, vintners, distillers, anybody, you know, in the alcohol business, people making alcohol hand sanitizer, they all use the density of solutions to figure out the percentage of alcohol in there because ethanol is less dense. But when we add a solid, when we add sucrose, it becomes more dense. So we're going to be looking at the change in density versus the concentration. So that's what a standard curve is. So if you have a standard curve, what are we going to use it for? So we have a standard curve. So we're going to make one. We're going to plot it. We're going to have our concentration here, and we're going to have our density here. What are we going to use this for? What's the point of having a standard curve?
To use it against unknowns.
Right. So now I have all these known concentrations. I plot them, and I get I get a curve. Now I have an unknown solution. What am I going to measure of the unknown solution?
The density?
Yeah, I'm going to measure the density. I can't measure the concentration because I don't know what the concentration is. I can measure the density, however. And so if I measure the density, how am I going to figure out what the concentration is? How does the standard curve help me do that? Right, Jovan. I compare it to the graph. What do I do with the graph? I have to use the graph for something. How am I going to use it though? What do you think? I'm going to compare it to the graph, but how am I going to use the graph? So Jovan suggests I use the density of the unknown, but then what do and see what the concentration is at that point. Right, that's one way to do it. So if my density is here, I just go across to my line. I see where where my density lands on that line, and then I go down, straight down, and then I see what the concentration of my unknown is. What's another method I could use? If I wanted to get a more accurate answer, what would be another thing I could do?
Are we going to know the volume?
Volume won't be important because we're measuring the density. So the density is grams over volume, mass over volume. So so we can just find the density on the y-axis, go to the line, go down to the x-axis and get our concentration. What's another method we could use to get a more accurate, just in case maybe we're plotting this by hand or something, and we don't have a really good straight edge or whatever. So Ferris, how would we go ahead.
Vaporize the solution and see how many grams is there.
No, I'm talking about we could do that. I'm talking about how do we use this graph in a different way to get a more accurate number for our concentration. Get the gradient of the graph. What do you mean by the gradient? I think I know what you mean. Density divided by concentration. And so we want to see what the relationship is between density and concentration. How do we get that? How do we get a numerical number for the relationship between density and concentration? Who's taken statistics or mathematics? What's the point of graphing something in the first place? What's one of the first bits of information you look for when you plot something? Right, you want to trend the slope. There you go, the slope of the line. The slope of the line, the slope of a straight line when you plot it is y over x. That is the density divided by the concentration. And so when you plot something like this, the slope of the line is going to tell you what the relationship is between the density and the concentration. And so you will get, hopefully everyone's going to graph this on like computers somewhere, either using Google Docs or Excel or whatever your favorite plotting program is. And when you plot a straight line, you get something called y equals mx plus b. B is where the line intercepts the y-axis. X is the concentration. Y is the density in this situation, and m is the slope. So if you plug in all those numbers, so I plug in my unknown density, I plug that in for the value of y. I know what m is. I know what the slope is. I know where the y-intercept is. The only thing I don't know is x, and I just solve for x. And that will give me a much more accurate determination of concentration, and then trying to eyeball it on a graph. So that we'll actually figure that out mathematically. Okay. So a couple of references here. This is where we're going to be doing the experiment. And then these two are basically just the exciting history of density measurements. Basically just tells you something about how density has been calculated over time. What's the uses of the calculation of density? Just because you have some of those questions, you can use those for background information. So let's look. So these are just a couple of the old instruments that I mentioned. One, I love the name of this, invented in Afghanistan like 1,000 years ago, the pycnometer, which is just basically a bottle of known mass and volume, and which is actually what we're going to be using today. We're going to be using a volumetric flask in order to measure exactly 100 mils and then measure the mass of that. So that will give us precise densities. And then hydrometers is a glass instrument that basically has a weight in it, like a slug of lead or something like that. And when you drop it into a solution, it will sink until it gets to a particular depth. And the depth that it sinks is dependent on the density. And so it has a number of marks on the side of it that give you the density of the solution. And it's often used for alcohol-containing solutions. So one group of measurements will be the density, and then maybe on the other side it will just be like percent volume by volume alcohol. If anyone's made homemade beer, you get one of these in order to figure out, how much alcohol is in your beer at the end. So they're still used to this day, and they're pretty accurate. That's called a hydrometer. So why don't we go to the website? This is the background here, where someone thinks they came up with the actual secret formula, and if they did, that would be worth quite a lot of money. But they found that 2.5 gallons of water contain 30 pounds of sugar. Now, one of the things we're going to do is make that and see what the density of it is. So we're going to make our standard curve, see what the density of formula X is, and then see if it is the same as the cola that's given in the lab. It's like typical commercial cola soda. Is it the same? Is it more? Is it less? So we're going to have to do some calculations to figure out 30 pounds of sugar and 2.5 gallons of water. Neither of those are metric measurements, so we're going to have to do some conversions for that. So first, we're going to make a series of standards. This is the whole standard curve part, where we take known amounts of our sucrose. So we take known amounts of sucrose, we weigh those precisely, put them in 100 ml volumetric flask, and then add water so that it comes up to exactly 100 mils, and then measure the mass. So that'll give us grams per 100 mils. And that is one of those mixed measurements that we talked about in chapter 6. Remember, we talked about, like, you see that a lot in like hospital environments where there'd be like, milligrams per mil or milligrams per 100 mils or something like that. In this instance, we're going to be looking at grams per 100 mils. The sucrose is pretty soluble. You can dissolve quite a lot of it in water. It's very polar. So we're going to make our standard curve, and then we will take out the known cola. Well, it's unknown to us, but like a sample, has a sample of cola there. We'll get a precise volume, we'll measure its mass, we'll see what the density is, go back to our standard curve and see what the concentration of sucrose is in it. The other bit of information that the website gives us, it actually gives us the exact concentration in molarity. And so what we can do is see if does our measurement of the concentration of sucrose agree with this concentration, and then we're going to figure out what's our error in determining that. Okay. So any questions before we go to the website? Is everyone able to get there? Ariana's got there. That's good.
Yeah.
So it's working for everybody? Okay. Where is... I'm going to try and get there on my own. So there we go. So does everyone see the home screen on their screen now? Or is it a different? Do you see the lab screen here? Or is it something else?
I see the workbench, yeah.
Okay, good. All right. So this is one of those labs where it's pretty straightforward. I'm going to take you through a couple of things to do, but basically, yeah, it's just a matter of measuring things accurately and then changing your units. So let's just do a couple of these to see what we're doing. So this is a volumetric flask. So what's the difference between a volumetric flask and just a regular old flask? Let's look for a regular old flask. Actually, they don't have any regular old flasks here. Oh well. Anyway, difference between like a volumetric flask and just a regular flask kind of looks like this. Probably seen them in like 100 old sci-fi movies or old monster movies where, like, Dr. Frankenstein would be in his lab holding up a couple of flasks with different colored water in it with bubbles coming out of it. So that would be like a regular type of flask. And we use those basically to pour solids and liquids in, and we can shake them until they dissolve. They're good for that. But what would be the difference between that and this? Ariana says it's more precise. More precise for what?
It can precisely measure 100 mils of water. Sorry, the solution.
Yeah, I mean, there's a line here. So there's a line on a volumetric flask that indicates that you have precisely 100, and it will be written right on the flask. But generally, let's say something like 100 mils plus or minus 0.005 mils or something. And it'll also have something that says TC. And we haven't been in the labs. We haven't used a lot of these glasswares. But TC means it's to contain. It basically guarantees that it will contain precisely 100 mils of whatever liquid is in there if the meniscus comes up to that spot. And so remember, here's the line, and our meniscus should look like this. It should just be touched. The bottom of it should just be touching that line. That means you have precisely 100. You want the bottom of it to touch the line, not the top. So let's just use it real quick. Let me clear all this stuff out. So the first thing we can do is just put the volumetric flask. Whoops. I need to change back to mouse. Okay. Put the flask on top of the scale or the balance. I think they call it a scale. We call it a balance generally. And then what does tare mean? Anyone remember? We've used these before. What does tare mean?
Clear the mass of the readings to zero.
Right. It means it basically removes the mass of whatever it is I've just put on it. And so when I measure the mass again, it'll only be the mass of whatever is inside that thing and not both. It basically saves us a step of having to subtract. If we want to measure, if I wanted to put like 10 grams of sucrose in there, I don't then have to subtract the mass of the volumetric flask. So when I hit tare, it goes to 0. So now whatever I put in there, I'm just going to be measuring the mass of that. So let's just take the water and move that over. Now I'm going to add 100 mils, and we'll see if it comes up to the line. So 100.00 mils. Pour, boom. So you can see, whoops, let me go back. Anyway, you saw that the line was just touching the meniscus of the water. So that was precisely 100. And look at the mass given. So 100.00 mils of water gives 100.0000 grams. So this is our baseline. So this would be the first point we would calculate and put on our graph, because this is 0 grams per 100 mils is of sucrose, and the density is what?
Density is 1 grams per mil.
Yeah, 1 gram per mil. So that should be our first point, because actually what this gives us is our y-intercept, because when x is 0, the y-intercept will be 1. So when I plot that, x is 0, y is 1. So that's where the line is going to intersect the y-axis, right at 1. So now let's take that off and remove the liquid. And now we're going to add just right click on it and you can remove the liquid. Okay. Now we can add some sucrose. to put some sucrose in. Let's try. So we're going to do a number of different masses of sucrose per 100 mils. And I think I suggested 5, 10, 15, 20, 25, 30, 40, and 50, something like that. So you want to have lots of points on the line. One thing about standard curves I want to point out, it's probably be a good time to point that out. If I have a standard curve like this, so this is my concentration, and this is my density. What if the density of my unknown is out here? Can I just extend that line and figure out what the concentration is? Is that allowed? Can I do that? Jovan says, yes, he agrees. So I got one yes. Anybody else?
Yeah, I think so because the slope formula.
All right, we got 2. Nang says it will be an outlier. Interesting. So does that mean we can't use it? So Nang, you're saying you can't use our formula to figure out the concentration from there.
Yeah, I think we can use it.
You think you can or you cannot?
Cannot.
Cannot, okay. So we got 2 to 1. Who else wants to vote? Oh man, nobody else has an opinion? Come on. 3 people. Remember, there's no bad opinions, just bad people with opinions. You can, but you should do more tests. So Ryan says maybe. So I'll just put a little check mark there. So we got 2.5 to 1. I'll take one more and then I'll let you know what the answer is. Anybody else? We just need one more answer. Yes or no? Can I use this density measurement to determine concentration? It's outside my standards. What do you think? Don't be afraid. Put the slope level out. So Jovan points out that, is the slope going to stay the same? That is something that you don't know. And that is why you can't use that. In this instance, you probably could, because I think there's going to be a direct relationship between density and concentration in a straight line all the way to, basically you get to a supersaturated solution where you can't add any more solute. But in the classic example where we're measuring light absorbance versus concentration, so that would be, actually, let me put up a new screen. When we use a measure the light being passed through a solution versus its concentration. It is linear at low concentrations. So at low concentrations, there's a direct linear relationship between the concentration of whatever it is I'm measuring and the absorbance of light at a particular wavelength. The more concentrated it is, the more light it absorbs. The more concentrated, the more light it absorbs. And then it goes out and out and out. But eventually, it stops being linear and just becomes the same. Because basically now it can't absorb any more light. It's absorbing all the light it can. And so once we get to there, we cannot use this measurement. So if I measure, so if I have a solution and my absorbance is out here, I can't use that. What I would do then is take that particular solution and dilute it by like 2 or 3, so that when I measured the absorbance, it would then be there. That I could use to figure out the concentration. But see, when you make a standard curve, you can't guarantee that it's going to be linear outside of the points that you measured yourself. You can't guarantee that. So it could go like this, it could go like this, it could go like this, and then like that. You don't know. So basically all you can guarantee is inside the measurements you did yourself. So if it's outside of that, you can't use it. But as someone suggested, you could make more standards to extend that further. In fact, that would be the thing to do. So that's why I sort of suggest going outside of the concentration slightly. Oops. Let me go back to the screen. Okay. So when we left off an hour ago, we're going to add 5 grams of sucrose. So let's put in 5.00 grams. So I'll pour that in. So now should have 5 mils or 5 grams of sucrose. Then add some water. Now notice I can't add 100 mils now. If I add 100 mils, that's going to go over the top, because in the solution, the sucrose is going to take up some space. So if I add 100 mils, it's going to be 100 mils of water plus whatever volume the sucrose is. So I don't want to do that. So what I'll do is put like 90 or so. And then I'll look and see on the volumetric flask down here what my volume is. Where is my annotation? Okay. Yeah, so notice here, it says I have less than 100. So basically what I can do is add an amount of water that takes me directly to 100. So it's 6.823. Actually, I'll add 6.8. See how close I get. You see, I'm super, super close. When you look at the flask, it is almost, but not quite up to that line. So to top it off, I'm just going to add another very, very small amount. 0.06. That's pretty much close enough. All right. So, and then I just weigh the flask. Put it back on the scale and read the mass. So now my mass is 101.860 grams. What is the density? What's the density of that solution? Has everyone gone to sleep? What's my density? I have a mass, but I'm not going to be plotting mass. I'm going to be plotting density. No one can tell me what the density of the sucrose solution is. So Jovan, what are the units? So I heard it was 1.01863. But what are the units? No, that is incorrect. Oh, wait a minute. No, that is correct. Sorry. Yes, grams per mil. Our density is going to be in grams per milliliter. So our first point we're going to plot is our concentration is 5 grams per 100 mils. That's the concentration. And our density is 1.01863. So do the same thing for 10, 15, and 20, and 25, and 30, 40, and 50. That should give you more than enough points to give you a nice straight line. And the density of the cola solution will fall somewhere in there. So let's have a look at the cola solution. So let me get rid of that. Now, one thing that this didn't do particularly well is when we go to the stock room, when we go to solutions, here we go. So here's our generic cola. Look and see, they didn't give us over 100 mils, because the way you would actually do this in the lab is that you would measure precise volume in a volumetric flask, and then you would determine its mass. Well, you can't do that here because the smallest volumetric flasks they have is 100. So you can't use it, which was sort of dumb on their part. So we're not going to use a volumetric flask. What we will use is a graduated cylinder, which isn't as good, but what are you going to do? So we have a 50 mil graduated cylinder. So go back to our stock room, get our scale. Here. Oh, I need to remove something. Here we go. So my workbench is not full.
Remove the water.
Should be able to have more things than that. Weird. Okay, so I take my graduated cylinder. I will measure the mass. You can see it's heavier because typically the glass of a volumetric flask is pretty thin because you don't use it. You don't use it for shaking. You're not making solutions in there, so it's generally quite thin. A graduated cylinder takes a lot of abuse. People are constantly pouring stuff in it and emptying it, and banging it against things. So the glass in the graduated cylinder is much thicker, so it's heavier. So we'll tare it, and then I'm going to put 50 mils of my cola in there. 50.00. And then just want to double check and make sure that the meniscus is on the 50. And it looks like it's on the 50. So measure the mass, determine the density, and then go back to your standard curve and use the slope of the standard curve to determine the concentration in grams per 100 mils. Okay, because right now there's water and there's a bunch of other stuff in there. We need to know how much sucrose is in there. So we can't just tell by we need the density for us to figure that out. That'll give us a concentration in grams per 100 mils. Now, one thing I mentioned was that you actually get the concentration of sucrose. If I click on the cola, you can see here that it gives you the concentration right there. It doesn't tell you what the unit is, and that's not very clever on its part, but it is molarity. So that is how many moles of sucrose there are in 1 liter of solution. Now, what you need to do is to convert grams per 100 mils into moles per liter and see if you get the same answer. Basically, what it is it's a determination of how accurately you can measure, how accurately you can measure the density, and B, how good a job you can do fitting that line in order to determine the density. And also gives us an idea, is density a good enough way to determine the sucrose concentration, or is there a better way to do it? That's one of the questions I ask on the post lab. Make you think about it a little bit. Is this a good way? Is this an accurate way of doing it? If you find out that your molarity is almost exactly the same, it's probably a pretty good method to use. If it's a lot different, maybe there's a better way of doing it. Another thing I want to point out is, what do you think of what would be the pH of this cola?
Seven.
Yeah, it'd be 7. Is that accurate?
No, isn't water 7?
Yeah, water is 7. What would be the pH of a carbonated beverage? Would it be lower than 7 or greater than 7? And why?
It doesn't ionize at all, so it wouldn't be hydrogen ion or hydroxide ion.
What doesn't ionize?
The sucrose.
No, the sucrose doesn't ionize, no. But what does carbonated beverage mean? What does that mean?
Carbonate. Oh,
What's put into the water to make it carbonated? What does that mean, carbonated? Does that mean carbon's put in it? Like charcoal's put in that?
the carbon dioxide.
Right. Carbon dioxide is the carbonation. So we put a lot of carbon dioxide in the water. And what does that make?
Carbonic acid.
It makes an acid. It makes carbonic acid. It's a weak acid. It's a weak diprotic acid. And so we put a weak diprotic acid into water, and it's going to release H+. So is like, even when you taste a soda, it tastes different, right? It tastes, even if it's just carbonated water. On your tongue, you should be able to tell that it's not a neutral pH. Will the pH be higher or lower than 7?
Lower.
Yeah, lower. It's acidic. All carbonated beverages are acidic because they all have carbon dioxide added to them, which make carbonic acid, which releases protons, which lowers the pH. So that's why people who have like bad tummies shouldn't drink a lot of soda, because it increases the amount of acid in your stomach when you've had more than enough already. So yeah, so the pH they've got there is it's not even close to being right. So basically, what this would be if you had completely flat cola. If you store it long enough, basically all of the carbon dioxide will be released from the water, and then it'll go back to being neutral.
Excuse me.
Yes.
What is dye here? The dye.
Oh, dye would be making it the color that it is. Probably caramel, some sort of caramel color, some artificial color.
Okay.
So that's the concentration of the dye in molarity. So there's not a whole lot in there. But yeah, every soda's got some sort of either natural or artificial color in it.
Okay.
Yeah. So go back to, make your standard curve, and that should be fairly straightforward. And let me go back to the online lab. So make your standard curve. So you'll using, so here's the ones to use. I gave you 5. So use so 10, 15, 20, 25, 30, 35, 40. And I'm almost certain, I think the cola is the same for everybody. The density of the cola will fall in between there. So you won't have to do more determinations. It'll fall within, it'll be somewhere in there. So you can determine, from the density, to be able to determine the concentration. Also, what I want you to do is make the formula X. So formula X has 30 pounds of sugar and 2.5 gallons of water. So convert that down to grams of sucrose in 100 mils volume. And then, so actually that would be 30 pounds. That's the tricky part. Is it at 30 pounds of sugar and 2.5 gallons of water, or 30 pounds of sugar and 2.5 gallons of liquid? Interesting. Yeah, so I guess that would be pounds of sugar in that amount of water. It makes a solution, and then measure the mass and the volume of that. That will give you grams of sucrose in 100 mils. Determine its density, then determine its molar concentration of sucrose. See if it's the same as the cola we just did. So basically it's asking, is it the same concentration of the cola that we just made? So is everyone clear on what it is we're trying to do here?
Sweater.
So what I think I'm going to do is just step out for, I don't know, 10 or 15 minutes, and then come back, see if you guys are working. You can talk back and forth, see what you want to do. If you have any questions, I'll check in before we call it a day, rather than
You
just
use
leave.
Excel, right?
Yeah, I use Excel. But you don't have to use Excel. Basically, anything that will give you a trend line. Make sure it's linear, because you should get a linear response. Because you can fit lines with all different kinds of things. You want to have a linear fit, because you want to wind up with y equals mx plus b. B should be 1, as we've mentioned, because at 0 amount of sugar, your density is 1. So that should be the y-intercept. And then you can figure out all the concentrations from the densities. Yeah, so your data table should look something like this for each concentration. Put in the mass, calculate the density. Then when you get to the unknown cola, volume, an accurate volume, accurate mass, and then give all these different densities, all these different concentrations. So grams per 100 mils, molarity, and mole fraction. See if you can remember what mole fraction is. And then we know what the molarity is because it's given to us. I think it was like somewhere around like 0.6 mole or something like that. See what your concentration of molarity is and see how close they are. You should have a pretty good error measurement. And so in the post-lab questions, the same thing for formula X. How close is formula X to the cola that is here? See how close it is. So if people want to go, they can. People want to stay. I'm going to step out for a minute, come back, and then see if you're working on it and have any questions. So any questions before I step out for a minute? Is everyone good?
Yes, thank you.
All right, I'll see you in about 10 or 15 minutes.